Imagine stepping onto an airplane, settling into your seat, and as those massive engines spool up, you realize you're not just on a machine, but essentially, well, a flying, interconnected supercomputer.
It really is something else.
It's a marvel of modern engineering, isn't it? But have you ever stopped to truly think about what it takes to get such an incredibly complex piece of technology safely off the ground and soaring through the sky?
Mm-hmm.
Today, we're taking a deep dive into exactly that, focusing on one of the most technologically advanced aircraft flying, the Boeing 787 Dreamliner.
And our mission for this deep dive, you could say, is to explore the cutting-edge innovations that make the 787 so unique, and then, crucially, the equally complex challenges that can arise,
Right.
particularly during critical flight phases like takeoff and climb.
Yeah.
Our insights today come from two main sources. A foundational technical description of the 787's core systems, the nuts and bolts,
Yeah.
and a recent analysis looking at specific operational issues this advanced aircraft has faced.
So get ready. We're going to uncover how this modern marvel is built, how it's powered, how pilots interact with its advanced systems.
Yeah.
And then we'll unpack specific real-world challenges related to its automated thrust and flight guidance.
It's quite a story.
It's a journey into the heart of modern aviation. So let's kick things off with a fact that might surprise you about the 787's construction.
Okay.
Over 50% of its structure is made of carbon fiber reinforced plastic, or CFRP solid laminate.
That much. Wow.
Yeah. When you think about the immense forces and aircraft experiences, consider what that means for its fundamental design.
It's a foundational shift, really. The core insight here. Well, this composite material allows the aircraft to be significantly lighter,
Right.
which directly translates to far greater fuel efficiency and an extended range.
Makes sense.
The 787 was designed from the ground up as a two-engine long-range airplane, built with ETOPS, that's Extended Operation Certification.
So it can fly those long ocean routes.
Right. Exactly, far from land. It comes in three main models: the 787-8, Next 9, Next 10. They vary in length, passenger capacity.
Okay.
The 787-8 flies 8,200 nautical miles with up to 210 passengers. The NAC 9 covers 8,000 nautical miles with up to 265, and the NAGS 10 manages 7,000 nautical miles for up to 295 passengers.
Impressive ranges.
Yeah, and all models share the same impressive wing design. It allows it to reach a service ceiling of 43,100 feet and a max operating airspeed of 360 knots.
And what's interesting is how that fundamental design choice, using so much composite, also trickles down to the passenger experience.
Oh, definitely.
It allows for things like a lower cabin altitude, just 6,000 feet, which feels much more like being on the ground, reduces fatigue.
Right, less pressure difference.
Along with increased humidity for better comfort.
Yeah.
Plus, those famously large cabin windows
Yeah, everyone notices those.
make for a much more open feel, and the pilots get impressive large format flight deck displays.
Exactly. These innovations are all part of an overarching design philosophy. It's known as integrated modular avionics.
Integrated modular avionics.
Okay, what's truly remarkable here is that this isn't just about combining different systems. It's about a deep integration of both the aircraft's avionics, its electronics, and its airframe systems.
So everything talking to everything else.
Pretty much. This demands handling vast quantities of data and intensive processing, which actually eliminates a large number of separate traditional hardware units, LRUs they used to call them.
Line replaceable units.
Exactly. The result: less weight, lower cost, and significantly increased reliability across the board. It's like moving from a room full of individual desktop computers to a sleek, integrated supercomputer.
So if that's the integrated modular avionics approach, how does the aircraft manage all that information? Is there like a central brain, or what's the core architecture?
That would be the Common Core System, or CCS.
CCS, okay.
It's an enhancement of that integrated modular avionics technology. It provides common computing resources for an incredibly wide array of airplane systems.
Now what?
We're talking everything from electrical power and environmental controls to cabin services, fuel, fire protection, even water and waste systems.
Wow, okay.
Think of it as the plane's central nervous system and brain all rolled into one. Its main components are two central computing cabinets, CCRs.
Common computing resources.
You got it. Then there's a super fast common data network, the CDN,
Right.
and 21 remote data concentrators, or RDCs.
Okay, so distributed intelligence too.
Exactly. This data network uses advanced protocols, ARNC 664, which is essentially like a dedicated fiber optic internet for the plane.
Fiber optics, wow.
Yeah, allowing critical information to zip around at up to 100 megabits per second. These RDCs, they act as interfaces, converting signals from various other systems like CAN bus or older ARNC 429 into the common network language.
So they translate.
They translate. They're dual channel too for redundancy. But this level of integration, well, it raises a key question. How does all this interconnectedness impact the plane's behavior, especially when something needs troubleshooting?
That's a crucial point. If everything is so intertwined, a small glitch could have ripple effects.
Absolutely.
Let's explore that by looking at how the 787 manages its power, because that's another area where integration takes center stage.
Definitely.
The 787's electrical power system is truly different from previous Boeing models. For example, it famously has no engine pneumatic bleed extraction except for cowl anti-ice.
Right. That's a huge departure.
That's a significant change in how core systems are powered.
It absolutely is, and the implication is profound. Far more systems on the 787 are now electrically powered.
The more electric aircraft concept.
Exactly. And because over half of the airplane's structure is composite, which, unlike traditional aluminum, cannot naturally conduct electricity to return current.
Ah, right. Composites don't conduct well.
The 787 employs a unique current return network, or CRN. It's made of aluminum and titanium.
Okay, so a dedicated return path.
Yes, this system is critical. It provides the return paths for all that electrical power and also protects against high-intensity radiated fields, external interference, basically ensuring the plane's digital systems aren't scrambled.
So, with so many systems running on electricity, what about the sheer scale of power needed to make this more electric aircraft fly? Where does it all come from?
The 787 has an impressive array of power sources designed for incredible redundancy. You have 4 powerful variable frequency starter generators, VFSGs, on the engines.
4 on the engines alone?
Oh, yeah, 250 kVA each. Then there are 2 more large generators on the auxiliary power unit, the APU.
Right, for ground power and backup.
Exactly, ASGs, 225 kVA each. For emergency situations, there's even a ram air turbine generator, the RAT.
The little propeller that drops out.
That's the one. Pops out to provide backup power, 10 kVA, if everything else fails. And of course, 2 lithium-ion batteries, main and APU.
Lithium-ion, interesting choice there too.
It is. Plus, 3 external power connections for ground operations. It's a truly robust and distributed power grid in the sky.
And it's not just the sources, but how the power is distributed, right?
Yeah.
I understand they use an innovative remote power distribution system, RPDS. How does that work differently?
That's right. Instead of huge centralized distribution panels that require miles of heavy wiring running throughout the aircraft.
Right, tons of copper.
The 787 routes power both 115-volt AC and 28-volt DC directly to 17 remote power distribution units, RPDUs.
17 of them.
17, strategically located throughout the airplane's length. These RPDUs then supply power to individual components nearby.
Closer to where the power is needed.
Exactly. The real innovation here is that this significantly reduces the amount of wiring and, critically, the overall weight of the airplane. It demonstrates a fundamental shift in how power is managed, making it lighter and more efficient.
So given all this electrification and integration, how do pilots interact with these highly digital systems? I imagine it's a completely different experience than older aircraft.
Oh, it is.
For example, are traditional circuit breakers even still a thing, or have they gone completely digital on the 787?
That's a great question because it is a very different experience. Pilots manage the electrical system from a dedicated panel on the P5 overhead,
Okay.
overseeing everything from batteries to external power, generator drives. And you're spot on about the circuit breakers. The 787 uses electronic circuit breakers, ECBs.
ECBs.
A huge departure from the old mechanical pullable ones. Their status, whether they're closed, open, tripped, or maybe locked out, or even unknown, is displayed right there on the multifunction displays, the MFDs, or it can even be accessed via a maintenance laptop.
So no more reaching up and resetting breakers manually.
Not in the same way, no. It's a cleaner, more integrated way of managing the electrical backbone of the aircraft.
Here's where it gets really interesting. Stepping into the 787's flight compartment, it's clearly designed for 2 pilots, 2 observer seats, building on the successful technologies of earlier Boeing aircraft, like the 737NG, 777, but with significant safety enhancements, increased capability, reduced costs. What immediately stands out for the pilots in this new setup?
What's immediately noticeable are the large, clear displays. Pilots have dual head-up displays, HUDs.
HUDs, okay, like fighter jets.
Exactly. Projecting critical flight information directly onto a transparent screen in their line of sight lets them keep their eyes looking outside more.
Yeah, very useful during approach and landing.
Absolutely. They also have vertical situation displays and very large format map displays. These can show terrain, weather, flight paths up to 1,280 nautical miles away.
Huge range.
Yeah. All of this critical information is presented on 5 large 12 by 9-inch flat panel liquid crystal displays. It gives an incredibly comprehensive and intuitive view.
How does the plane communicate all this vital information, especially if something's going wrong, to the crew during a flight? I imagine it's designed to avoid overwhelming them.
That's precisely the challenge, and it's handled by the Display Crew Alerting System, or DCAS.
Yeah.
This system is designed to provide clear visual, audio, and even tactile alerts, like a stick shaker for non-normal conditions. It uses a critical, color-coded hierarchy to prioritize information.
Color-coded, okay, like red means.
Red alerts are warnings displayed right at the top. They require immediate crew action, often with a distinct oral warning like a bell, siren, or maybe a voice alert.
Got it. Urgent.
Then you have cautions, which are amber, shown below warnings. Require immediate crew awareness, maybe not immediate action, but you need to know. They usually have a beeper sound.
Okay.
Below that are advisories, also amber but indented. Just for crew awareness, no sound. And finally, communication messages and memo messages, both white, sometimes with chimes, just reminders or status info.
So it filters the noise.
Exactly. The crucial point is that it precisely prioritizes information to ensure pilots know instantly what demands their attention and how urgently without being flooded by less critical data.
It sounds like a lot of information coming at them potentially. How do the multifunction displays, the MFDs, help pilots manage it all and dive deeper into specific systems if needed?
Well, the flexible design of the flight deck allows several of the large displays, the inboard ones and the lower center one, to function as MFDs.
Okay, they can switch roles.
Right. This means they can show a variety of information. Critical engine data, EIC's navigation displays, electronic checklists that guide pilots through procedures.
Checklists right on the screen.
Yep. And perhaps most powerfully, they can show dynamic synoptic pages.
Synoptics, what are those?
They're graphic representations of systems, like the electrical system, hydraulic, flight controls. They use colors to indicate conditions: green for normal, amber for caution, etc.
Ah, like a live diagram of the system.
Exactly. These various displays are easily accessed via dedicated control panels, the EFI ZSP, and multifunction keypads, MFKs. Gives the crew an incredibly comprehensive, integrated view of the aircraft's health and performance at all times.
So with all this incredible integration and sophistication, here's the pivot. What happens when even small pieces of the puzzle don't fit perfectly, especially during those most critical phases of flight, takeoff and climb?
Yeah, the high workload, high risk phases.
We're talking about potential malfunctions in the takeoff go-around, or TOGA mode, the autothrottle, and the full authority digital engine control, FADEC systems.
These phases are absolutely critical because they demand precise coordination of engine thrust, airspeed, pitch guidance, everything for a safe ascent.
Right.
When these systems malfunction, the risks are severe. You could see insufficient thrust, maybe asymmetric power where one engine goes high and the other doesn't.
That sounds dangerous.
That can be.
Yeah.
Or even a complete loss of climb performance, any of which could be hazardous right after liftoff or during a go-around.
Okay, let's dig into these three vital systems and their interaction, because that's where the complexity really comes into play, isn't it?
Yeah. Absolutely. Let's break them down. First, the TOGA system. Its purpose is pretty straightforward. Provide increased engine thrust for an optimal climb during takeoff or a go-around.
Okay.
It's activated by switches on the thrust levers. Pushing those engages the autothrottle for a programmed thrust setting and activates the flight director for pitch guidance on the displays.
Got it. Then the autothrottle system.
Its role is to automate thrust adjustments to maintain desired airspeeds or thrust settings. Hugely reduces pilot workload, especially in climbing crews.
Okay.
Now, what's crucial here is a nuanced point. While the autothrottle doesn't directly rely on the Low Range Radio Altimeter, the LRRA, for its primary function.
The radar that measures height just above the ground.
Exactly. The LRRA indirectly influences some flight modes, like determining the thresholds for activating go-around mode based on height above ground, so its accuracy matters.
I see. And the third piece, FADC.
FADC. This is the direct digital engine controller, like the engine's own computer. It continuously adjusts parameters like thrust, fuel flow based on inputs from the autothrottle, pilot commands via the thrust levers, and the flight management system, the FMS.
Okay, the final executor for the engine.
Right. And a key detail. FADC has its own protection logic, preventing overspeed or overtemp, but it will execute thrust commands within its validated limits, even if those commands were based on faulty upstream data.
So if it gets a bad command from the autothrottle, it might just do it.
If the command isn't completely out of bounds, yes, it assumes the input is valid.
So what does this all mean when something goes wrong? How could these sophisticated systems designed for safety become a liability in a specific scenario?
It creates a critical vulnerability, a potential chain reaction. Imagine a false LRRA reading.
The radio altimeter fails or gives bad data.
Exactly. It tells the plane it's, say, only 5 feet off the ground when it's actually climbing through 500 feet. This erroneous data can mislead the autothrottle logic. Some modes might interpret this low-altitude reading as meaning the aircraft is landing or very close to the ground.
And if it thinks it's landing?
It might command the engines to idle thrust, like it would during the landing flare.
Oh no, not during climb out.
Precisely. The FADTC, faithfully following this command because it's technically within limits for idle, would execute it. This could lead to a dangerous loss of climb performance right when maximum thrust is most needed.
Wow.
It really highlights how a single incorrect sensor input can cascade through these highly integrated systems with potentially serious consequences.
That's quite a chain reaction.
Yeah.
So what are the common causes of these types of malfunctions in the 787 that could lead to such a critical situation? Has this happened?
Well, operational data and analysis have identified several contributing factors. These include, as we discussed, erroneous thrust commands, potentially stemming from faulty autothrottle logic or incorrect LRRA inputs. Then there's asymmetric thrust if the autothrottle fails to synchronize engine power properly, or if one thrust lever doesn't move as commanded.
One engine roaring, the other lagging.
Right. Also, what's known as mode confusion or pilot error can play a part. Maybe selecting the wrong mode or inadvertently double pressing the TOGA button, which can sometimes cause unexpected behavior. Hardware or interface failures are also possibilities preventing thrust levers from advancing correctly. And sometimes a delayed crew response to subtle issues like a slowly developing thrust asymmetry can exacerbate things.
And environment.
Yes, environmental factors like hot and high conditions, taking off from a high-altitude airport on a hot day, already reduce engine performance margins, making any thrust issue more critical.
So a combination of factors can create a perfect storm.
Potentially, yes.
So how is the industry responding to these specific identified risks? What's being done to make sure these highly integrated systems function as intended, especially given the scenario you just described with the LRA?
The industry, particularly regulators like the FAA and Boeing, have implemented several proactive and mandated measures. A crucial one is a recent FAA Airworthiness Directive, or AD. It's 2024-1607.
An AD, okay, that's mandatory.
Yes, mandatory. It requires a software update effective October 23, 2024 for all Boeing 787 models, the NAGNA 8, NAGNA 9, and NAGNA 10.
And what does the software fix?
It specifically corrects those autothrottle logic errors that could be triggered by erroneous LRRA inputs. It addresses potential thrust anomalies during takeoff, climb, and balked landings, affecting the thrust management, or TM, and displays and crew alerting DCA systems.
Directly targeting that scenario.
Exactly. Compliance is required within 6 months of the effective date.
Okay, what else?
Beyond the AD, there's operational guidance, a special airworthiness information bulletin, SAIB Air 2019, and a flight crew operations manual bulletin, TBC 108.
SAIBs and bulletins, right?
These provide flight crews, actually for both 787s and 777s, which share some similarities, with procedures for managing autothrottle anomalies and reducing risk during these critical flight phases. Better awareness, better procedures.
Training and procedures.
Yes. And there are related Boeing service bulletins mandating specific software installations and other ADs, like one from 2020, mandating certain system maintenance procedures, such as regular power cycles for the Common Core system, the CCS, to ensure its health.
So software fixes, updated procedures, specific maintenance, a multi-pronged approach.
Exactly.
So what does this all mean for you, the listener, and for the safety of air travel, knowing how incredibly complex these systems are and the proactive steps being taken?
It means that strict compliance with these directives, the software updates, the procedures, is absolutely essential. Consistent maintenance is key, and active pilot vigilance during critical flight phases remains paramount.
Human oversight is still crucial.
Absolutely. This multifaceted approach, combining software updates, operational training, and rigorous maintenance, is essential for maintaining the inherent reliability and continuously enhancing the safety of the Boeing 787. It's a constant evolution to keep these flying supercomputers operating at their peak.
The Boeing 787 Dreamliner is truly a testament to incredible engineering, seamlessly integrating this vast array of systems into a complex and incredibly efficient machine.
It really is.
But as this deep dive has shown, with that complexity comes the need for continuous vigilance, precise software, and robust procedures to manage the unforeseen.
And the aha moment here, I think, is really understanding how a single sensor input like that from a low-range radio altimeter, something seemingly small,
Yeah.
can have cascading effects through highly integrated systems such as the autothrottle and FADEC. It just underscores the critical interplay of hardware, software, and human factors in modern aviation.
And the response shows commitment.
Absolutely. The industry's proactive response with targeted software updates, operational training, it highlights a profound and ongoing commitment to safety in an increasingly integrated world. They learn, they adapt.
So here's a final thought to leave you with. As aircraft become even more integrated and rely even more heavily on common computing resources,
Which seems to be the trend.
what new frontiers will we see in aviation safety, and how might the relationship between human pilots and these, well, flying supercomputers continue to evolve in the decades to come?
That's the big question, isn't it? Where does that balance ultimately lie?